Hello students, welcome to a session with time. Today we are going to discuss this concept ozonolysis, which is usually encountered in organic chemistry. So part of chemistry, part of organic chemistry. So before we begin, I want you all to note our YouTube channel Time for IITJEE NEET, wherein you will find interesting videos covering various important concepts expressed or explained in a simplified way. So shall we begin? Now this is a small topic, ozonolysis, and this is the first part. So we are going to discuss a few aspects under ozonolysis involving organic compounds. So shall we begin? Now, before we take up the actual ozonolysis, let us check what are the frequent questions that a student is bound to ask the teacher or ask himself or herself. What are the compounds that undergo ozonolysis? Now we'll give a response to this. Now, compounds that undergo ozonolysis need to have a multiple bond. Multiple bond could be a double bond or a triple bond, which means that there is unsaturation. So the first part is being answered. Ozonolysis is happening on those substances which have unsaturation. Unsaturation means a C double bond C or a C triple bond C, only between the carbons. The multiple bond is between carbon atoms. Next, what are the different types of ozonolysis? Now, when the student reads ozonolysis, he finds that different reagents are being used in addition to O3. O3 is definitely there because ozonolysis needs ozone. But in addition to ozone, there are certain other reagents added up. For example, zinc. They may come across acetic acid. They may come across H2O2. They may come across methyl sulfide. So like this, the student is bound to face some issues here. What are all these reagents going to do? So different types of ozonolysis, right, will have different combinations of O3. Right, either O3 with zinc or acetic acid or methyl sulfide will give one type of ozonolysis, and O3 with H2O2 is going to give a different type of ozonolysis. Ozonolysis with zinc and acetic acid or methyl sulfide is called reductive ozonolysis. We'll check what these are. In fact, today's session will concentrate mainly on the reductive ozonolysis. There is also an oxidative ozonolysis, which we'll take up in the forthcoming sessions. So the second question is also being answered for the student. Different types of ozonolysis are reductive or oxidative, and they can be done on alkenes or alkynes, because there is a C double bond C in alkene, there is a C triple bond C in an alkyne. Now, how many products are expected from ozonolysis? Now, this part we will not be able to answer now because it depends upon the starting material. So, what is the reactant? What type of reactant is it? Is it cyclic or acyclic? Once again, let me clarify that in this session we are going to cover only acyclic compounds undergoing reductive ozonolysis. I hope this is clear. So the third question will be answered, or students might get to know within this session, but then we are putting this aside because this is not something that we can answer immediately. Next, how to identify the starting material by looking at the products. So while we are doing this session, we are going to do this. So this is being done. This I am not going to comment now, right? While a student by himself or herself will get to know this, right? Then, how to identify whether the starting material is cyclic or acyclic? Even this we will take some time, right? So I have answered the first two questions simply, right? So the remaining questions will take some time. A student might understand in this session itself, or in the forthcoming session will be able to throw light on that. So shall we begin? What is ozonolysis? Now ozonolysis requires ozone. Ozone is going to react with what? An alkene or an alkyne. Then we have got a combination either with zinc, acetic acid or methyl sulfide or H2O2. So ozone adds to an alkene. It could be also alkyne and forms corresponding ozonide. It's an ozonide. Reaction of ozonide with zinc dust and water. This is what we talked about, one combination, or zinc and acetic acid, or even methyl sulfide, right, will give what? Aldehydes and ketones. So you'll get aldehydes and ketones depending on the structure of the alkene. So ozone is adding up to an alkene or an alkyne to form an ozonide, alkene ozonide or an alkyne ozonide, and then subsequent treatment is with zinc dust and water, or zinc and acetic acid, or even methyl sulfide, right? That part is called reductive ozonolysis. So when you have only these combinations, zinc or acetic acid and water or methyl sulfide, it is reductive ozonolysis. When you are using hydrogen peroxide, we will be having oxidative ozonolysis. So this part we are not going to take up this session. Let it be clear there. Now so far I think it is all clear, right? What is a reductive ozonolysis? What is an oxidative ozonolysis? So we have covered the types of ozonolysis. Next, if the double bond bearing carbon has hydrogen atoms, at least one hydrogen atom, then the product is an aldehyde. Product or products will be aldehyde. If it has alkyl substituents, there is no hydrogen, then it is a ketone. So they found out that if you have a double bond, so we have started with only a double bond, means alkene, right, is the focus now. If it has at least one hydrogen, we get an aldehyde. If there is no hydrogen, we get a ketone. Is that clear? Now ozonolysis helps us to locate the multiple bond, whether it is a double bond or a triple bond, C double bond C or a C triple bond C. We can identify, we can locate its position, and from there we can get the parent hydrocarbon, right? Whatever alkene which underwent ozonolysis, what all the products we got, from there we can identify the parent hydrocarbon. For example, we could identify whether it is but1-ene or but2-ene. So are we not able to locate the multiple bond? Multiple bond, that is double bond, is at position 1, double bond is at position 2. We can identify, is it not? So ozonolysis helps us to locate the multiple bond in a given hydrocarbon, parent hydrocarbon. I hope this is clear. Now this is what is the main thing that we started out with. How to identify the parent alkene from its product of ozonolysis. Now let us look at this. Now we have got ozonolysis being done, right? And this workup means taking out of this compound and treating it separately, right? So here we are actually using zinc and water combination, which you have not shown here, right? But please note. So here the products you have found out, this plus this, there's a plus here, there are two compounds formed. Look at the products and decide what is the starting material. So this is the parent alkene. So how to get the parent alkene from the product that you have got? We have got two products which are carbonyl compounds. In fact, they are ketones. Now look at the starting material and the products. If I am able to remove the two oxygens from here and attach the two carbons with a multiple bond, that is a double bond, am I not getting the parent alkene? So how to get the parent alkene? By simply removing the two oxygens and then attach the two carbons holding the oxygen with a multiple bond, that is a double bond here. So by looking at the product, by removing those two oxygens and attaching the carbons which had those oxygens attached, we are going to have the parent alkene, right? So this is a simple technique that we will use to get the parent alkene out of the products of ozonolysis. I hope this is clear. So we'll see some more cases and test our knowledge. But just before that, let us recall what has been told in the previous slide. We said when alkyl groups are attached, we get a ketone. Here, this is an alkyl group, this is an alkyl group, so we got a ketone there. So ketones are obtained when you have alkyl groups, when you don't have any hydrogen. If you have a hydrogen, you'll get an aldehyde. At least one hydrogen, you'll get an aldehyde, right? So let us keep that in mind and then move on and check whether what we read is correct. Now let us look at this. Now this carbon is having two hydrogens, and what we need to do, simply break the C double bond C and on either side put oxygen, isn't it? How did we get the parent alkene? By removing the oxygens. How to get the products? By putting the oxygens, breaking the double bond and attaching the oxygens to the carbons that had the double bond between them. So we have got, so wherever you have got a hydrogen, that will give an aldehyde. Here at least one hydrogen is there, you still have an aldehyde, right? So this part is one carbonyl compound which is an aldehyde. This part is another carbonyl compound that is an aldehyde, because it has got a hydrogen, at least one hydrogen is there. Now we said how many products of ozonolysis are formed, that we will see as the session happens. Now this is an acyclic hydrocarbon, it's an alkene, it's acyclic, it is not cyclic. If it is acyclic, if it is not cyclic, we get for every double bond a product. There is one double bond here, so you get two products on either side of the double bond, right? We attach the oxygens and then get two products. So if it is acyclic, we get two products, right? And as we move on, we are going to see what if the starting material is cyclic. Let us look at this case. Again, there are two hydrogens here, put an oxygen attached to the carbon. So this becomes methanol. So it is an aldehyde here again, because there is a hydrogen. There are two hydrogens in fact. Here, let us look at this. There are no hydrogens, therefore you get a ketone. So on this part, we have got two methyl groups and therefore there is a ketone formed. Let us look at the third case. Again you have one hydrogen, so you are bound to have an aldehyde. You got an aldehyde. CHO means aldehyde, isn't it? Whereas here, I have attached the two oxygens. I have got alkyl groups, so I get a ketone. Now coming to the fourth case, which is cyclic. 1, 2 and 3 were acyclic and we got two compounds for each double bond. Here you have a double bond. Break the double bond again in the same fashion that we mentioned. Put an oxygen there, put an oxygen here. But then you got only one compound. So if there is a double bond, a single double bond in a cyclic structure, you are bound to have only one compound. You don't get two compounds. Two compounds are formed only when it is acyclic, when it is open chain. When it is closed chain, you get only one compound. So part of your question that we started out with is being answered. Part of your questions that you had at the beginning, right? One by one we are taking up and then trying to address them and then give response to that. I hope this is clear. All the four compounds that we started out with, it's a reductive workup. Means you had a zinc water or acetic acid or methyl sulfide. Methyl sulfide by itself can function instead of zinc to do reductive ozonolysis. So all these are reductive ozonolysis examples. I hope this is clear. Now we have few more cases to check. Let us do that. This is ethene. Break this bond, attach one oxygen, attach one oxygen. So this is a formaldehyde formed. This is a formaldehyde formed. So one more thing that we are going to note here. Is it a symmetrical alkene? It is a symmetrical alkene. A symmetrical alkene, even if it is acyclic, it will give only one compound. It will give 2 moles, but of the same compound, because it is a symmetrical alkene. An alkene which is symmetrical will give only one compound. Keep that in mind. In the previous examples, we had taken alkenes which are not identical, which are not symmetrical. So, they are all different here, is it not? Whether it is compound 1 or 2 or 3, right? They are unsymmetrical alkenes. Means the alkene cannot be broken into 2 identical parts. They are all unsymmetrical alkenes. Unsymmetrical alkenes will always give 2 products. It could be aldehyde-aldehyde or aldehyde-ketone or ketone-ketone combination, but you will get 2 different compounds if you start out with unsymmetrical alkene. But here we have come up with a symmetrical alkene. Ethene is a symmetrical alkene, therefore there is only one compound. So, one more question is being answered. How many products we asked? If it is an open chain alkene, right, it is acyclic and it is symmetrical, you will get only one compound. But that compound will have a molecular formula which will be having half the number of carbons, because one molecule is this and the other molecule is that. So, one molecule is split into 2 equal halves, therefore, each half will have half the number of carbons, correct. Propene is an unsymmetrical alkene, therefore, it will give 2 products. Put this side 1 oxygen, that side 1 oxygen. This is methanol or formaldehyde, whereas this is ethanol or acetaldehyde. So, 2 different compounds. So, 2 compounds we got. 2 compounds we got because it is an unsymmetrical alkene. I hope this is clear. And now we are dealing with a cyclic substance, which we already did in the previous case. 1 oxygen there, 1 oxygen here, and then you have got just 1 compound. A cyclic is giving only 1 compound. 1 compound of same number of carbons. Keep that in mind. So, suppose there is a question saying that an alkene or an unsaturated substance gives 1 compound on ozonolysis, then it could be either a symmetrical alkene or a cyclic or cycloalkene. But then one more data regarding what is the molecular formula of the compound will make it clear whether it is acyclic symmetrical or a cyclic symmetrical. I hope this is clear. Cyclic compound for that matter, not necessary to be symmetrical. So, when you get just 1 compound, look at the molecular formula of the compound. If it is half, then it is an open chain alkene. If it is same number of carbons, it is a cyclic alkene or a cycloalkene. I hope this is clear. Understood? Now, let us move on to the mechanism of ozonolysis. I am showing it only for an alkene here, which you can extend it to an alkyne too. Now, this is ozone with the central oxygen being positive and one terminal oxygen is negative. A singly bonded oxygen has a negative charge, a doubly bonded oxygen has no charge, a triply bonded oxygen has got a plus charge. Clear? Now, this is a mole ozonide formed which is unstable. It has to get stabilized. How it will get stabilized? This CC bond is going to break, right, and form a C double bond O, and this will come out as a minus charge. That carbon which was about to become positive is stabilized by the lone pair on this oxygen, which is what you have shown here. Clear? So, after that has got broken, so this is this, I'll put the things which are exactly present there. So, I can take this as a CH3, this as a hydrogen, that as a CH3 and this as a CH3. It is as if that we are answering the previous mole ozonide, right, turning into a set of 2 compounds. Then what has happened? This minus charged oxygen attacks a carbonyl carbon, right, which has got split actually. Before it splits, this minus will attack that. That O with the pi bond will attack this carbon, and then you will get back the lone pair on oxygen. Clear? I can show it here. Now that C double bond O with the two bonds here, and this C with a double bond O with a plus charge and a single bond O with a minus charge, and then two substances attached, so two substituents attached, CH3 and CH3. Now this is going to attack this carbon, and with that pi bond it is going to attack that carbon, and then this pi bond will give back the electron density on oxygen, that is a lone pair on oxygen, and then we'll get the ozonide, which is stable. This is a stable ozonide, right? This one is stable, down. This ozonide is stable. This ozonide will be treated with zinc, water, acetic acid or methyl sulfide combination for a reductive ozonolysis. Lysis means what? Breaking of the bond. So that now the ozonolysis part is formation of ozonide followed by lysis using any of the reagents that we mentioned. Clear? This is for a triple bond that we have shown, right? It should be clear enough what we showed for the double bond, right? The same thing. The only difference is that this bond will still exist. If it was a double bond, there will be no bond existing. Because it is a triple bond, one bond exists, and you got an ozonide, which is stable ozonide. In alkene, you did not have this C single bond C. Now you have the C single bond C because you have started out with a C triple bond C, not with a C double bond C. Clear? So this is the stable ozonide formation from an alkyne. So far, though we have discussed only alkene, right? We have discussed the alkene mechanism in detail, and therefore we are able to extend that particular mechanism to an alkyne, and the mole ozonide, which is also formed in an alkyne, will turn into a stable ozonide. Clear? Now this is the stable ozonide that we had written there. Now this is methyl sulfide doing the job of reductive ozonolysis. So ultimately what happens, that we'll see now, right? All these is, I mean, a part of the mechanism that we have shown. So this methyl sulfide sulfur is attacking this oxygen, that O becomes O minus, back polarizes, you get a double bond, and this becomes a minus here, and then you get a benzaldehyde here, right? And the remaining part will also be another benzaldehyde because it's coming from a symmetrical ozonide. And then whatever methyl sulfide you got, that became DMSO, dimethyl sulfoxide. So the dimethyl sulfoxide is a polar aprotic solvent which you are using for SN2 reactions, right? That we know very well. So this is the mechanism using sulfide, methyl sulfide, dimethyl sulfide. So dimethyl sulfide will turn into dimethyl sulfoxide at the end. Now this is for an alkyne, sorry. Now in this is the oxidation part, oxidative part. This is the reductive part. So this is the oxidative part. So an alkyne on reductive ozonolysis gives a dicarbonyl compound, single compound. An alkyne also gives a single compound on reductive ozonolysis. So you have this bond still existing. There were three bonds, two bonds are gone, one bond is still remaining, and you got a dicarbonyl compound. This is oxidative ozonolysis. So this part, if you break, I put a hydrogen there and put an OH there. So this will become a carboxylic acid. That will also become a carboxylic acid. Clear? So two carboxylic acids you get upon oxidative ozonolysis. A dicarbonyl compound on reductive ozonolysis and two carboxylic acids upon oxidative ozonolysis. I hope this is clear. So this is for an alkyne. Oxidative ozonolysis, as we said, is not part of our first session, though in this we have included. We'll take this up in more detail in the coming session. Clear? Next, let us look at some questions wherein what all knowledge we had gained so far would be put to test. Which compound would give 3-methyl-6-oxoheptanal on ozonolysis? Sir, let us put this structure. Heptanal 1, 2, 3, 4, 5, 6, 7. Number the carbons 1, 2, 3, 4, 5, 6 and 7. 3-methyl, so you have a methyl group there. 6-oxo, so you have a double bond O there, right? Heptanal, HO. So you have a C double bond O here actually. So between the first carbon and the sixth carbon, you need to have a double bond, because I will remove this O, I will remove that O and attach the two carbons which had the O's. So first carbon and sixth carbon are going to be attached. Or let us take the products here and then check which one will give the required product. So I'll break this O and O. There is a hydrogen here which I have not shown. So take this as carbon number 1, 2, 3, 4, 5, 6 and that is 7th carbon, CH3. So is it not the same compound that we are looking at? This is giving 3-methyl-6-oxoheptanal, right? So CHO, there is a CHO here, CH2, CH2, sorry, CH3, this one, right? And then the remaining parts are giving us the same compound that we wanted. Suppose I break it here with an O, this is a hydrogen here, and an O here. This is carbon number 1, 2, 3, 4, 5, 6, 7. But on 5th carbon there is a methyl. We want it on the 3rd carbon. So this is out. Look at this, break this. You have a hydrogen here. This is carbon number 1, 2, 3, 4, 5, 6, 7. Any question why we are putting carbon number 1 on the carbon that is having the hydrogen? Because it is an aldehyde. It's going to give an aldehyde. Aldehyde has got more priority over ketone. So here, where is the ketone? The ketone is there on the 6th carbon, but we have, sorry, methyl is there on which carbon? 6th carbon here, but we have methyl on the 3rd carbon. So even this is not true. Look at this. Again, there is a hydrogen here. Again, this is carbon number 1, 2, 3, 4. On the 4th carbon, you have got the methyl. So this is also not true. Therefore, it is the first compound. Clear? Which of the following statements is incorrect with regard to ozonolysis? It would involves as ozone addition on alkene, correct? It also involves on alkyne, but does it not involve addition of ozone on alkene? Yes. An unsymmetrical alkene gives two different carbonyl compounds, true. That is what you have seen. Symmetrical will give only one. It is used to identify the number of double bonds in a starting material. Yes. We have seen the location, right, of a double bond. It can be used to detect the position of the double bonds. So this is the one which is an incorrect statement. Ozonide will undergo cleavage by zinc water. Yes, this is ozonide formation followed by what? Lysis. That is how it becomes ozonolysis. Clear? So option D is the correct answer, which is incorrect statement. Now, ozonolysis followed by treatment with zinc water of cis-but2-ene gives ethanol. Yes, let us check. Cis-but2-ene. So C double bond C, right? But is cis means carbon, carbon, hydrogen, hydrogen. Break this O, ethanol, ethanol. Yes, statement 1 is correct. The product obtained by ozonolysis followed by treatment with zinc of this compound has no chiral atom. Let us check that part. Oct4-ene. Oct means what? 1, 2, 3, 4, 5, 6, 7, 8. Number the carbons 1, 2, 3, 4, 5, 6, 7, 8. 3 and 6. On the third carbon there is a methyl, on the sixth carbon there is a methyl, and on the fourth carbon there is a double bond, right? And you're going to break this. We'll have an oxygen here, we'll have an oxygen there. Now this is a hydrogen here on the third carbon, hydrogen there on the sixth carbon. The sixth carbon has got a methyl, an ethyl, a hydrogen, and a carbonyl CHO. So it is a chiral carbon. Sixth carbon is a chiral carbon. In a similar way, 3 is also a chiral carbon. Having no chiral carbon is not true. Statement 1 is true. Statement 2 is not true. In fact, statement 2 will give us what? 2 moles of CCC with a hydrogen, with a methyl, and with a CHO. So this becomes what? 2-methyl butanol. 2-methyl butanol has got a chiral carbon. There are 2 such moles, right? So statement 2 is wrong. So shall we say option 4 is correct? Statement 1 is correct, but statement 2 is incorrect, right? So if you find that you need some time to note this, please do that. Then I'll bring in the remaining part of the statements, right? So 2 moles of this we have got, and the second carbon is a chiral carbon because it is having 4 different groups attached. No chiral carbon is not correct. So option is 4. Next, which of these alkenes on ozonolysis gives a mixture of ketones only? So check this, break this. You have a hydrogen, you have an aldehyde. You have a hydrogen, you will have an aldehyde. So 2 moles of ethanol, not correct. Break this. There are 2 hydrogens here, aldehyde. There is 1 hydrogen here, aldehyde. So both are aldehydes. Here also both are aldehydes. The first one is also both aldehydes. So not true. Break this, you get a ketone here, double bond O. That is also a ketone and a ketone. Mixture of ketones. 3 will give. What about 4? 4 has got oxygen here and an oxygen there, but this part and this part are same. It's a symmetrical alkene. So only 1 ketone you got, did not get a mixture. This is a mixture of ketones. Clear? So only 3 gives a mixture of ketones, not 4. Though 4 also gives only ketones, but the 2 ketones, 2 moles of the same ketone is being formed. Clear? An alkene on ozonolysis gives methanol as one of the products. It has to be only 1 hexene because 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So on the first carbon there is a double bond, hex 1 in. You break this, you will have O and O. So this is methanol. So if methanol has to form, the double bond has to be there on the first carbon. It cannot be on the second carbon, cannot be on the third carbon. Again 1 heptene. 1 heptene can also give, let us check, 1, 2, 3, 4, 5, 6, 7. Again a double bond there. Again you will have formaldehyde formed or methanol formed. So this will also give, that will also give, not B and C. Methanol is one of the products. Yes, methanol is one of the products in both 1 hexene and 1 heptene. I hope this is clear. Now ozonolysis of 2,3-dimethyl 1-butene followed by reduction with zinc and water gives. So 1, 2, 3, 4. This is carbon number 1, let us say. 2,3-dimethyl. This you are going to break. There is a hydrogen there. There is a hydrogen here. Oxygen, oxygen. So this is methanol. And this is what? This you can number as carbon number 1 here. 2, 3, 4. So on the second carbon there is a double bond O. So it is 3-methyl butanol. Clear? So what do you have? C and a C. That C has become double bond. As it is, I have put the carbons, right? And there is a carbon here. So if this is carbon number 1, that is 2, this is 3, this is 4. So this part is what? This part is butanone. On the third carbon there is a methyl. So 3-methyl butanone, and then you have methanol formed, that is formaldehyde. Now that is all for this session. As I said at the beginning itself, you can subscribe to this YouTube channel. You will find interesting videos, right, covering various concepts that you will be needing for your entrance exams, right? Entrance exams of various kinds. It could be state, it could be central, it could be JEE main, it could be CUET, it could be NEET, it could be state engineering entrance exams. So many, BITSAT, right, VIT, SRM, Manipal, so many. So these are all our details which you can note and then get in touch with us. Make us part of your successful journey. Thank you. Best wishes.